Okay, in this video we are going to introduce the fundamental quantity that we call temperature. And the first question that comes to mind is, what is temperature? And to show what that is, let's just show you a little simulation that I have here. And so here we have a container. This is a container, and then we are going to create a gas. Uh, we're going to add some molecules inside. So now we have some molecules, and those molecules, they have some energy. They are moving, right? And so they have kinetic energy. They are bouncing off the walls. That those collisions with the walls, that is what creates the pressure. And they have each one of these molecules have kinetic energy. So now let's add some energy in the form of heat, right? So we add some energy, and now you can see here that the temperature is increasing. What that is doing now is making the particles move faster. So we are going to relate temperature to this energy per particle, how much kinetic energy the particle has. So this is a good picture to have in your mind. The temperature is related to the kinetic energy of the particles. Okay, let's go back to our slides now, and then so the temperature is related to how much thermal energy there is in a system, and it is also related to the kinetic energy of the particles that we saw in the simulation. For now, until later, until we are able to define this properly, we are going to say that temperature is what we measure with a thermometer. Here you have two thermometers, and you can see one is measuring uh, ice and the other one is measuring water. And then you can see that they have two different readings, and this reading here is what we are going to call temperature. So there are three scales that are important for temperature: the Celsius scale, the Kelvin scale, and the Fahrenheit. The Fahrenheit is what we use here in the US, and this is the conversion from Fahrenheit to Celsius. The Kelvin and the Celsius scale are similar. The only thing that changes is where you put your zero. For the Celsius, the zero is at the freezing point of pure water. That would be your 0 degrees, and your 100 degrees is the boiling point. For the Kelvin, you just add 273 and then you get the Kelvin scale. So the 273 would be the freezing point of water. And the Kelvin has the nice property that it can give you the temperature at absolute zero. There is a temperature, there is a minimum temperature that you can ever reach, and that temperature is zero in the Kelvin scale and is minus 273 in the Celsius scale. So these are some important points for different materials, and here you have the three scales. For instance, the freezing point of water is 0 in Celsius, is 273 in Kelvin, and is 32 in Fahrenheit. The normal body temperature is 37 in Celsius, is 310 in Kelvin, and is 99 in Fahrenheit. The boiling point of water is 100 in Celsius, 373 in Kelvin, and 212 in Fahrenheit. And the melting point of iron, you can see that it's very high here. And the absolute zero, this is another important one, is minus 273, 0 in Kelvin, and minus 460 in Fahrenheit. So which is the largest increase in temperature of these five? Choose the one that you think is appropriate here. Take a minute. And B and C, because they have the same scale, the only thing that changes is your zero. They would have, these are the same, and they have the largest increase in temperature. So let's talk about absolute zero. and temperature. And one experiment that you can do is that you have a container, right? And then you have this bubble here that you fill with some gas, right? And then you start cooling the gas and you measure the temperature of this thing here. And then you plot that. And when you plot that, you get a graph that is something like this. You have the temperature scale here and the pressure here, right? You measure the pressure as you cool down, and then you can do it for one type of gas, and you'll see that it's going all the way down here. And you can put a different gas, say neon, then you put argon, then you put oxygen, and then you do the same, right? So you just go all, you just start cooling down and measure pressure and temperature, and you plot those numbers. And for the three gases, here you see that they all converge to this point. This point is what we call the absolute zero of temperature. You cannot have less temperature than that. The temperature can never come down to this point. So this is your absolute zero. And that is the point where if you look at this simulation that we had here, the absolute zero would be the point. Let's just remove heat, remove energy, and cool down. So you can see it's coming down, 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 down. So if you remember that I told you temperature is related to the kinetic energy of the particles, you see that eventually when the particles have no kinetic energy, then you would have no temperature. That is your zero temperature. Now we are at 11 kelvins, 10 kelvins, 8 kelvins, 7, 6, and you can see they are almost not moving anymore. They are 3, 2, 1. So reaching zero is actually very difficult, but eventually you can see that they are going to stop. At, at the absolute temperature, which is very hard to reach experimentally, the particles just won't move. Uh, so that is a picture that we have to have in mind. Actually, it's not quite true that they'll still have some motion, but that we're not going to touch on that on this class. We're going to assume that they basically have no kinetic energy at 0 Kelvin. And that is a picture that we need to have in mind for this class. All right, so another important idea is that of phase changes, right? So we can go from solid to liquid to gases. And if we plot the temperature, if we say we take a solid and then we plot the temperature as a function of time as we heat up the solid, what you're going to see is that the temperature increases and increases and increases, but then there is a point where it just stays flat for a while. This is when the ice is melting. Then it's going to increase again, and then it's going to stay flat again for another time, another small time, and this is when it is becoming a gas and then increases again. So in these flat regions, you're transferring energy to the system, but the system is using this energy to break the bonds and go from a solid to a liquid. And here there is a similar behavior. Okay, thank you very much.